Welcome. Today we begin our new unit with the notes worksheet entitled Exponential Functions. This is just a nice introduction to exponential functions. We'll be dealing with a lot of great applications over the course of this unit, but we definitely want to lay that foundation properly here today. So we're going to start out with a couple investigations, one dealing with what's called exponential growth and one dealing with what's called exponential decay, and we'll see if we can come up with our model that we will highlight all unit long here. So some great math. You will need a calculator for this, so make sure you have one available, and let's give it a try. So these two, by the way, are as contrived as it gets, but I like them to really see the mathematics behind it. So here we go. You place $1,000 into each of two bank accounts. The first account is going to pay $70 at the end of each year. The second account is going to pay you 6% interest at the end of each year. Track the balance in the account over a 4-year period. Beautiful. Okay, I'll tell you what, let's do balance one first. Although I guess might as well just go ahead and put $1,000 into each of the two. So everyone, if you would, put $1,000 right in there. Now let's do, as I said, the easy one, which would be the first account. So the bank is going to add $70 at the end of each year. So nice and easy. In fact, I'm going to go ahead and try to put what's going on mathematically there. But I hope you all agree we're going to add 70, so you'd get $1,070 at the end of the year. Sounds good. At the end of each year, bank adds another $70. So add 70, and I'm looking at $1,140 right there. Okay, perfect. Same deal, just between years 2 and 3. Get another $70 at the end of the third year, $1,210. Okay, good. One more time around. What do you say we add 70? And I'm thinking $1,280 would do. All right, now notice in this case, this value, the balance in the account, is increasing by a constant amount every year. Keep that in mind because you're going to have to model that mathematically in just a little bit. Okay, so add $70 each and every year, get our new balance. No big deal. Shouldn't scare us at all. Now the second order of business is to kind of deal with this balance in the second account. It's a little different. They're not going to go up by the same amount, but what it's going to go up is by the same percentage. So what would that look like? Now just to help with the math here a little bit, I'm going to do just a little math off to the side. And then I want to figure out, just like this, great simple calculation, what can I do to the $1,000 to get the balance at the end of the first year? Then what can I do to that to get the balance at the end of the second year, and so forth. So bear with me for just a moment, and let's see if we can figure this out. So I hope everyone's clear. Let's just deal with the end of the year, where I had $1,000, and the bank is going to add to that. So either you're writing this down off to the side, or you're just looking at the screen, but make sure it really clicks for you. So you start with $1,000, and now the bank is going to add 6% of that $1,000. Is everyone okay with that piece? Perfect. Now, what I'm looking for is just a more efficient way to write that calculation. I don't want to have to write all of that in here. I want it smoother, cleaner, whatever you want to call it. And here's what I'm thinking. I have the 1,000 right here. I'm going to put a little 1 out in front, if that's all right with you. And I'm going to treat this just algebraically. So I have the 1 times 1,000 and 0.06 times 1,000. Does everyone kind of see this? Maybe thinking back from like the beginning of the semester, a little factoring. Do you see that there's 1,000 here and 1,000 here? Well, guys, I'm going to factor that out. I'm going to take out the 1,000, and what I'm left with when I take out the 1,000, I'm left with a 1 right here. There's this piece, and then a plus, and I took out the 1,000 from here, and I'm left with 0.06. Everyone kind of see that? That's kind of cool. By factoring out 1,000, I only have to write it once, and I get 1 plus 0.06, which as a matter of fact, here's my 1,000, and this is times 1.06 numerically. So do you see that this thing right up here, which I explained in quite a bit of detail, quite comprehensively, simplifies nicely to just this calculation right here. If I want the balance at the end of the year, all I have to do is take it and multiply it by 1.06. That's awesome. Okay, so that's exactly what I'm going to do. So everyone, if you would, can you write times 1.06? And can you grab a calculator? I'm going to do it as well. I want to make sure we see each and every one of these calculations. I'm going to take the 1,000 times 1.06. So again, this is you get to keep your 1,000, and they add 6% of the 1,000. They add $60 to it, and you get 1,060. All right. Now, wouldn't you be in agreement that if I asked you to do the balance for the next year, if you keep getting 6% to the previous amount, wouldn't I just go ahead and multiply this by 1.06, right? Because I would start out the same process. If I wanted the balance at the end of the second year, I would work over here, and in this case, though, I'd start with 1,060. And they're adding 6% to my 1,060. That's the key, by the way. They're adding 6% not of 1,000, but of a larger number, 1,060. And wouldn't I just go dot, 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 and come up with the same premise? So wouldn't I just be multiplying it by 1.06? You bet. And that's the key. So I am repeatedly multiplying by 1.06. So let's get that in place right up here. So I'm going to do, look, times 1.06. By the way, oops, that did not work. So let's do that again, 1,060. Geez, calculator does not want to, I'm not typing it in correctly. So let's go one more time. 1,060. Now I'm finally getting it there. 1.06. Whew, sweating that one out. It looks like 1123.60. Okay, nice. By the way, look at this. We earned $60 that first year, right? Did we earn $60 that second year? No, absolutely not. We earned more than $60 because, as I said, in this case, we took 6% of this. Take 6% of larger and larger numbers, our interest is going to start increasing too. Good. I hope everyone's now okay with the fact that we're going to multiply by 1.06 to get here, multiply by 1.06 to get here, and I could continue to do that. Let's fill this in. I'm having calculator issues, but I'll see if I can regroup. So times 1.06. Hey, got it. So there we go. I'll go dollars and cents on that. That would be 1191. How about 02? And then times, how about again, 1.06. And so about 1262.48, give or take. Okay, well, let's put them in. So 1191.02. Notice the interest is changing. The interest is getting higher and higher. And in this, by the fourth year, what's that? 1262.48. Could I keep going? Yeah, I think we've run our course though. So it's time to put this together. So I guess I'd ask you, could you write a function to model the balance in account 1? Then could you write a function to model the balance in account 2? 1 is going up by $70, add 70. 1 is being multiplied by 1.06. Wow, really awesome. Well, maybe you've tried this already. I'm going to do A for amount. If you want to do B for balance or just your basic Y equals, you're more than welcome to. Makes no difference to me. But it looked like this. I start with 1,000, and I'm going to add $70 repeatedly. Now, how do I go ahead and think about this? In terms of operations, everybody, repeated addition is what simplified operation. Repeatedly adding 70 is really doing what? Well, repeated addition is multiplication. So if I'm doing plus 70, plus 70, plus 70 every single year, what that really is 70 times the number of years. So I hope you're all okay with that. And notice this is a nice linear function. I know I just reversed the order, but guys, this is mx plus b. Your slope, so to speak, your increase is the $70 per year. Nice. Now, let's see what you remember from last year. Could you write a model based on this situation? Same deal, guys. You're starting with 1,000. Let's put the 1,000 in place. And I am repeatedly multiplying by 1.06. First year, second year, third year, fourth year. What operation, everybody, is repeated multiplication? Well, repeated multiplication is an exponent, and hence our exponential model. And there it is. So when it went up by 6%, I kept multiplying by 1.06. And repeated multiplication is an exponent. So if I multiply it 3 times over, it's raised to the 3rd. If I repeatedly multiply it 10 times over, it's raised to the 10th. Ah, that looks outstanding. Good. Let's go get the decay. Again, totally contrived, but I think the math really works out nicely. So number 2. You and a friend each buy a car for 20 grand, conveniently enough. Your car seems to depreciate in value by about $1,200 per year. Your friend's car seems to depreciate in value by about 5% per year. By the way, a typical car decreases in value by about 15 to 20% per year. So this really doesn't have any bearing on this problem. It's just, as I said, very contrived, but it's just to get the math. So what do you say? Let's start 20,000. No big deal. And let's go get the value of the car. So let's see how my math is here. In this case, are you okay? It seems the friend's car comes first. Nope, your car comes first. All right, so it's depreciating by $1,200 per year, so it's just going down by $1,200. So in this case, if it's going down by $1,200, how about $18,800, something like that? Okay, lose another $1,200. Let's be quick with this one. And how about $17,600? Okay, good. How about losing another $1,200? Get me down to $16,400. So keep subtracting $1,200. One more time just for good measure. How about by the end I'm at $15,200. End of story. Okay, not too bad. Not too worried about that piece. So it's going down by a constant amount. Now here's the key. And by the way, over the years I've seen students have a lot of success with exponential growth and struggle a little more with exponential decay. So let's be clear on how this piece works. Same idea with the math. So watch what happens. Let me write it out here. So your car, or your friend's car, I guess, is going down by 5% per year. So let's talk from year 0 to year 1. The value of the car starts at $20,000, and it's going to lose, so we're going to take away 5% of that $20,000. Everyone okay with that? So it starts at 20 grand, and we're going to subtract 5% of that 20 grand. That should give us the new value. Now, like I did before, everyone, I'm going to tuck a little 1 right out in front there just for good measure. And I'm going to go GCF on this thing. It's time to factor out with those two terms. I'm going to take out a 20 grand. And when I take out 20,000, interestingly enough, my parentheses, here I'm left with a 1. Now here's the key. It's not plus, it's minus, of course, 0.05. Everyone see that, factoring out the 20,000? And so what I'm looking for is a nice, quick, easy, efficient calculation to go from one year to the next. And it seems like I'm taking my value and multiplying it not by 0.05, that 5%, but multiplying it by 1 minus 0.05, which would be 0.95. Okay? So I hope everyone's comfortable with that piece, that in this case, if it's losing 5%, I'm really multiplying by 0.95. And that kind of makes sense when you think about it. When we're talking about the value of the car, if it's lost 5%, that means it's retained 95% of the value. So let's go for it. Here's my 20, 1, 2, 3, times 0.95. And of course, 19 grand. And not to belabor the point, would I perform the same mathematics going from this year to the next? Yes. Losing 5%, so I'm just going to multiply by 0.95. And let me get that in place and we'll do it all at once. Same thing here, same thing here. All right, if you're getting that idea, you're well on target. I'm just going to get a few numbers out. I don't know what I have here. So let's see, times 0.95. Let's get 1. Good, I'll try to keep that in the back of my mind. Times 0.95. Let's get another one. yikes, and times 0.95, and maybe get that last one. All right. Well, let's see. Let's see if we can get those values down. So let me do a quick look at them. All right. So I have 18,050, if I remember correctly. Yep, so 18,050. Then I have, let's see, 17,147 and 50 cents. I caught that one. And just real quick, sorry, just going to bring it up one time. There we go. Okay, so the last one there was the 16,290. And I already lost the cents, but heck, it doesn't matter. Well, I guess good measure on these notes worksheets. Got to be perfect. How about 13 cents? All right, good. Let's move on. Now here's the key. We've got the data in. I think I've moved past that. The question is, can you do example 2? So it says, write a function to model the value of your car. That's the one that's going down by 1,200. Write a write a function to model the value of your friends. That's the one going down by 5%. So here we go. I'm going to go V for value. Do what you want, of course. And we start with 20,000. And I am repeatedly subtracting $1,200. Or I'm really repeatedly adding negative $1,200. Repeated addition is multiplication. And in this case, I'm repeatedly adding negative 1,200. So how does that sound? And there's our slope right there, everyone. The rate of change going down by $1,200 per year. So multiply that by the number of years and tack that onto the 20 grand. MX plus B. Beautiful. That should fit right in line with a lot of modeling you've done over your math careers. Now the secondary piece, a little harder. Same deal. We're starting with 20,000 though. And the question, of course, is repeated multiplication is what operation? And if I'm repeatedly multiplying by 0.95, then it's 0.95 raised to the t. If I multiply 0.95 twice, it's raised to the second. Multiply 0.95 3 times, it's raised to the third. However many years have passed, that's how many times I would have multiplied my value by 0.95. And there's your exponential. Excellent. Okay. I think, let's see, describe the difference between an exponential model and linear. Let's go linear model first. Excuse my shorthand. So a linear model, as you saw, and as you know, increases or decreases by a constant amount. That's the slope, that's the rate of change. It's going up or down by the exact same value. So linear model increases or decreases by a constant amount. Something that is exponential does not go up or down by the same amount. Notice the value of the car is definitely changing when I keep multiplying these values by 0.95. Here it went down by 1,000, here it went down by 950, etc., etc. So it's not going down by the same amount when it's exponential, but it is going down up or down by the same something. And here's the key, guys. Please make sure you emphasize this piece. It increases or decreases by a constant percentage. And that's what we're going to look at. Quantities that increase or decrease by a constant percent are going to be modeled exponentially. That's wonderful. So in our 2 investigations, something about the balance going up by 6% per year, exponential. The car going down by 5% per year, exponential. Perfect. Let's go to the next board there. And yeah, here we go. Big asterisk. This is your unit in a nutshell. So exponential growth and exponential decay can be modeled with the equation, and you saw this in Algebra 2. There's your y equals a times b to the x. Okay, now don't write this on your paper, just kind of thinking out loud. Notice it fits that mold of what we came up with. Here was the exponential growth model for the bank or the interest. Y equals a times b to the x. Second one, the exponential decay, was the 20 grand times 0.95. Again, same deal. y equals a times b to the x. I'll leave them up for just a little bit here, and then when we fill these in, I'll probably erase it. So little a represents the initial quantity, what you start with. And if you look at the two investigations, you'll see that is the case. We started with $1,000 in the bank account. There's little a right there, little a. Value of the car started at $20,000. There it is right there. So little a is the initial quantity. Now the key, everybody, how about a little asterisk next to this? We'll be doing a lot of work with the b value. Some people call it a growth or decay factor. I'm going to call it a growth or decay rate. Again, either way, it doesn't matter. And so the b value is our growth factor or our decay factor. Obviously, one or the other. We'll talk about what makes the difference there momentarily. And it is equivalent to, here's what I have. So it's either going to be 1 plus the percentage or 1 minus the percentage. And so we do have to be just a little careful here. I'm going to write a couple things off on the side. R is the percentage rate. But we do have to be careful. Written as a decimal. Please be very clear on that piece. So it goes up by 6%. So the R was 0.06. Going down by 5%, so 0.05. Okay, so R is the percentage rate written as a decimal. And that's what we did here. I'll just write it in. Again, just kind of thinking out loud. Remember how we got that? 1 plus 0.06. There's your R. Remember how we got this one? 1 minus 0.05. There's your R. Cool. All right. Very good. So x and y would be the independent variable and dependent variable. Typically, not always, but typically when we talk about something exponential in nature, our model, x will represent the number of time periods. Again, not always. I can think of 1 or 2 exceptions to that, but the number of time periods. Something growing or decaying exponentially over time. Good. And then the dependent variable would obviously just be the amount after that many time periods. So the amount after x time periods. Really, it's just the quantities themselves. One independent, one dependent. Okay, great. And then I guess I'd ask you, if I gave you an exponential model and just you look at it and in a matter of seconds, could you tell me if it's growth or decay? So how can you tell one versus the other? It's all based on the b value. And here's what I have. If the b value is bigger than 1, because again, you'd be doing 1 plus r. So if the value is bigger than 1, then it's exponential growth, just like we saw here. Bigger than 1, exponential growth. Now we do have to be a little careful on exponential decay. Obviously it's going to be less than 1, but I think we want to be a little more clear on sort of the lower boundary. I would argue that you're not going to be losing more than 100%. You can't lose 100%. So I would argue that it's going to be between 0 and 1, long story short. So that's our case. And that's, you see this fit in right here perfectly. So bigger than 1, growth. Between 0 and 1, decay. And it's all based on that b value. Nice. What do you say we do a couple quick examples and round it out? So got this information online, population of Colorado. So the last last 50 years of the 20th century there. And 1950 to 2000, population of Colorado increased by about 2.33% per year. So does that mean that it increased every single year over the 50 years, exactly that percentage? No. This is what's called an annualized percentage. So when you take a look at all 50 years and you annualize the percentage increase, it comes out to 2.33% per year. In 1950, the population of Colorado was just over 1 million. So it says write an exponential model for the population in terms of time. Here we go. There's your notation in terms of the number of years since 1950. All right, here's where it would be great for a pause in the video and see if you could pull it off. It's one thing to watch me do it. It's another for you to be able to pull it off yourself. See if you can write the model. Well, here's what I came up with. My initial value was this right here. And if it's increasing by a percentage every year, and that's what we have, our annualized increase, 2.33%, then it is exponential. And the B value I got as 1.0233. And then that would be raised to the t, the number of years. So if we are repeatedly multiplying by 1.0233, then that's our base of our power right here, raised to the t. If you're not sure where that came from, let me just quickly off to the side. Remember, it's 1 plus the percentage. 2.33%. You move the decimal 2 places to the left. That is 2.33%. There you go. That's that. Okay. Make a prediction about the population this year. So this video is being recorded in 2013. So let's see. Year 0, let's be careful. Obviously, I don't want to put in 2013. We started our model in 1950. So 2013 would be year 63. So that's our t value. Good function notation right here. Population in year 63. So what I would theoretically be doing with a growth rate of 2.33% or the 1.0233, I would repeatedly multiply that 63 times. Easier than that is just to raise it to the 63rd. So let's see what we end up getting here. I'll go ahead and get my value. You do the same if that's all right. So 1,325,089, and then times 1.0233. Keep having issues down below here. So 1.0233. Make sure I have that right. Cool. Raised to the 63rd. And so let's see what we get here. I have about 5,654,000. We'll round up there, 998. So 5,654,998. 5,654, about 998, give or take. Wonderful. And you know, functions generally are fairly straightforward. When I give you an input, you can come up with the output. Nice. Now it says here, use a graphing calculator to predict when the population could reach 6 million. So again, just according to the model that we've created, a little outdated because we're dealing from 1950 to 2000. But you know, I'll bet you this is relatively close. And if we were to continue with that 2.33%, when could it reach 6 million? So I'm looking for something like this. I hope everybody is in agreement, where I'm giving you the output and you're coming up with the input. Now it should be noted that you can and probably have solved something like this algebraically in Algebra 2. Because I haven't taught it just yet, I can't hold you accountable for doing that. But as we go through the unit, you'll be able to, and chances are it'll be easier than the way I show you with the graphing calculator here. But for right now, we're going to have to use the technology to pull this off. So here's how we're going to do it. We're going to do it graphically. And again, if you know how to solve for t, I won't stand in your way. I won't help you with it just yet because I want to save that piece. But I'm going to go ahead and graph it. So what I'm going to do is actually graph the function. So I'm going to put a little y1 right here. And I'd encourage you to kind of do it this way, at least at the outset. So what I'm going to do is basically put in the function into the y1. And what I want to know is, when is that function going to get up to 6 million? So in the y2, everybody, I'm going to just type in 6 million. And this allows the calculator to come up with a way where you're trying to find the x for a particular y. And what we're going to do is see where they intersect. So just write that piece down. Again, you're going to probably have to do this for me a few times over, so get comfortable with it if you would. Well, let's go ahead and see. I bring my calculator on up and I go to the y equals, and let's see if I can have some success typing this in. 1,325,089, and what do we say? Times 1.0233. 0.0233 raised to the x. Absolutely perfect. Now what I want to know is, over the years, how long would it take for us to hit 6 mil? And make sure I've got my zeros. Looks good. Now don't just hit graph because that wouldn't make a whole lot of sense. Again, think about it. X is the number of years. Y is the population. Now we are only obviously talking to the future here, so I mean I'm going to start at 0 even though we probably shouldn't even do that. And I don't know, I mean we're already above 5 million. I'm going to go 100 years out. I don't think we have to go that far. So, you know, just a century from the beginning of the model. And then this is the population. Obviously population can't be negative. So I'm going to go ahead and throw a 0 in there. Again, not that it matters. We know the population starting in our model is 1 million. I like starting at 0. That's just me. And we have to get up to 6 million. I like leaving a little buffer just so it's not all the way at the top. So I'm going to do 7 million. But whatever. Again, guys, window is totally arbitrary. I'm going to hit graph, though, and let's see if it worked. By the way, if you remember from last year, nice exponential curve getting steeper and steeper. And there's our 6 mil straight across. And you can see there's the number of years right there. So the way this works with the technology, hit second, trace, go to intersect. How about just an enter, 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 and there we go. So about 65.5 years, give or take. And that's when it hits the 6 million, excuse me. So I think I saw about 65.57 years. Guess kind of translates into 2015, give or take. Wonderful. Given an output, can you find the input? I hope you can. Hope you can make it happen. All right, good one right there. Last good application problem from here today, and again, over the course of this whole unit, we'll be seeing tons and tons of applications dealing with exponential functions, and then soon, logarithmic functions. All right, here we go. China's one-child policy was implemented in 1978 with the goal of reducing China's population to 700 million by 2050. Here's the key. In 2000, so this is where we're going to start our model, by the way. Yikes, I think I got rid of something there. Let's try to do it a little better. There we go. So in 2000, the population was about 1.2 billion. And again, I think we want to keep everything in millions here. So I just wrote it on your paper for you. 1.2 billion would be 1,200 million, just FYI. So suppose that China's population declines at a rate of 0.5% per year. Will this rate be sufficient to reach its goal? Well, what do you say we start our model in 2000? Because that's the first population that we're given here. I know they started in 1978, but we don't really have the 1978 population. So let's write a model first, then we'll figure out how to answer the question. So beginning in this year right here, it looks like our initial value is going to be the 1,200 million. Yeah, it's just easier than keep it in millions than writing all those zeros out for 1.2 billion. All right, now here is the key. Would love to see you pull this off. What's the B value? Be great for you to pause and try it out. What is the B value if it's declining at a rate of 0.5% per year? Well, I got one, and I'll show you how I got it in just a sec. I got 0.995. That was my B value, and hence my model. And the way I got that, of course, is first and foremost, 0.5%, get rid of the percentage symbol, move that 2 to the left. That is 0.5% right there. Now the way the B value works, it's going to be 1 minus the R. So 1 minus 0.005. And so as a result, there's your 0.995. Okay, just be very clear. That percentage has to be written as a decimal, especially something like this. I could see students overlooking that. Be careful on that. Okay, well, let's see. We start with 1.2 billion. It's going to go down by 0.5% per year. Is it sufficient to get to 700 million by 2050? We could do it output to input or input to output. I think obviously input to output is quicker. So what do you say we find the population after 50 years of doing this, and does it hit that 700 million? I don't know. Let's find out. So 1200.995, and let's see if that goes into effect for 50 years, declining at that rate, and let's see, do we get to 700 million by that time? I'm going to bring the calculator up one last time to do this calculation. Yep, not on here, of course. There we go. 1200 and times 0.995 raised to the 50th. Whew, not even close. Still have, well, at least it's under $1 billion, but well over the target of 700 million. So I'm just going to do this, about 933. I caught 0.9 something. No, we shouldn't do that. I'll just truncate it out there, million. And so the answer is a whopping no. Okay, very cool. If you have questions along the way, please don't hesitate to ask, but really want to be quite comfortable with that y equals a times b to the x. A lot of good work goes into that model. Hey, of course, as usual, thanks for listening, and hopefully, well, if I can clarify anything, you just let me know.